So far we've seen two equations. We've seen an equation about acceleration, A equals V minus U over T, and we've seen an equation that shows us displacement. We've seen a half times U plus V brackets T. I would just like to kind of standardize these symbols. We have the T, which might be the most obvious one, that stands for time. Then we've got the A, this is also quite easy, acceleration. We've got the V, which stands for final velocity, and then there's U, that stands for initial velocity. Now, the whole time I've been talking about displacement, I've been labeling it with just a DISPL, but the symbol we're actually using in mechanics to represent displacement is an S. It would be like that, something like that, displacement. So these are the symbols that we'll use to represent these important things. S for displacement, U for initial, V for final velocity, A acceleration, and T time. And in general, I like to call, or I was taught to call these formulas the SUVAT equations. Just flip that over. So displacement, initial velocity, final velocity, acceleration, and time. So let's see the two formulas that we've looked at again using those symbols properly. So we've seen one formula that looks like this: A equals V minus U out of T. And we have one that looks like this. Now, instead of writing displacement, I'm going to write S equals a half U plus V brackets T, something like that. And so this equation here has acceleration, velocity, initial velocity, and time. But I would like to have a few equations that include displacement but also include acceleration, or I would like to have equations that include initial velocity but do not include final velocity, just to quicken my working. So these are the equations we're going to try to derive in this lesson. However, instead of using this equation in this format, instead of using it in the format A equals V minus U over T, we're going to make V the subject, and we'll make V the subject to actually be something like V equals U plus AT. I did something like this a while back, and you can follow through the math and you'd be able to get to that. So let's look at the first equation we want to derive. So for the first equation, instead of using a U, we're going to substitute the U with, we're going to make U or V the subject, and then eventually we're going to make T the subject. So we've got this equation: S equals a half U plus V brackets T. We want to make an equation that maybe does not have the V in it. How can we do that? So S equals a half U plus, well, we already have V written out in another format. We have V equals U plus AT. So we can write V as U plus AT, then brackets T. We have that. So if we continue this, we have S equals to a half times U plus U, that's 2U, plus AT, the two brackets T. Continue a little bit more, we'd have it looking like that so far. Then we continue with this: S equals a half of 2U plus AT. So S will be equal to, now we're going to expand out that bracket. We'll have S equals to a half of 2U, we're going to multiply the T by that, 2UT plus A, well, T times T will be T squared. Now I'm going to multiply everything by what's inside the bracket. When we multiply half times 2, that gives us 1. So S will be equal to UT, just 1 UT, plus when we multiply half times AT squared, we'll actually just have a half AT squared. So this equation will help us to easily calculate any of these things shown. So displacement, initial velocity, time, or acceleration, without requiring final velocity. but we can make a bunch of new formulas just starting from the very first two formulas. Let's look at another. We again have v equals u plus at, and we have s as a half u plus v brackets t. This time I want to make u the subject of the equation, so I'm going to come to this equation right there, and I'm going to move the at to the other side. So I have u is equal to v minus at. I'm just getting this at and moving it to the other side. So u is equal to v minus at. U equals v minus at. So this means I can come here where I have u and replace u with v minus at. So s will be equal to a half v minus at plus v. Let's collect like terms. We'll have s equals a half v plus v is 2v minus at bracket t brackets time. So if we continue with this, we'll expand the bracket with a t first. So we'll have a half 2vt minus at squared. And then if we continue with that, we'll have s being equal to vt minus a half at squared. And that will be the second equation that we can form with that. And then we're going to form one more equation, starting again from just those two equations. So our two equations are v equals u plus at, and the other equation was s equals a half u plus v brackets t. So this time we're going to replace the t. We have v equals u plus at. Let's first make t the subject. V equals u plus at. If we're to make t the subject, we're going to first of all move the u to the other side to have v minus u equals at, and then we're going to divide through by a to isolate the t. That's what we'll actually end up with, is something like v minus u out of a equals t. So now we can get that and put it in a place of t in this first equation. Let's just remove this. So we have a t right there. I'm going to substitute it with that. So we have t is equal to v minus u out of a. So I'm going to substitute that. So have s equals to a half u plus v, and then v minus u brackets over a. So the first thing we can do is to first of all remove these two denominators, the a half and the a. So if we multiply this side by 2a, then we'll also have to multiply this other side by 2a. So on this other side we'll have 2as is equal to, well, this 2 cancels out with this 2, and this a cancels out with this a, is equal to u plus v brackets v minus u. Let's just expand this out. So we'll have something that looks like a bit like this. 2as equals u times v is uv, u times negative u is minus u squared, v times v is positive v squared, and then v times u is negative v u. So next we'll have is 2as equals to, let's get the positives in the first place, v squared plus uv minus vu minus u squared. Now since multiplication is commutative, and that just means a times b is the same thing as b times a. That means if we have vu, we can actually rewrite that as uv. So we can actually just rewrite this as uv. And when we have uv minus uv, this just cancels out. So now what are we left with? We're left with 2as is equal to v squared, and then there's the minus u squared there at the end. So what we're going to do for this is that we're going to move the u squared to the other side, where it will become a positive. So we'll have 2as like that, 2as is equal to v squared, and then we're going to get this u squared and take it to the other side, become positive u squared. So our final equation will be v squared is equal to u squared plus 2as. That will be the final equation. Now I'll just write down all the equations just for memory. V squared equals u squared plus 2as. We've got s equals ut plus a half at squared, and then we've also got s equals vt minus a half at squared. And then we had the original equations, which were v equals u plus at, and the second equation, which was s equals a half u plus v brackets t. The only important thing to remember about these equations is that they only work when your acceleration is constant. We said acceleration is how much your speed changes. So if your speed is changing by the same amount each time, say you're adding on in 1 second, you are moving at 0 meters per second, then the next second you're moving at 2, then 4, then 6, and your speeds are increasing like this. That means every second you add on a speed of 2 meters per second. Consistently your speed increases by 2 meters per second, or maybe your speed decreases by 2 meters per second, and then you had -2, maybe -4. This means you're going in the backwards direction. This is the only position where these formulas will work. The moment you don't have the acceleration being constant, these formulas kind of fall apart because they are built on the assumption that acceleration is constant.